Okay, so I last time we went over this simple model of gases that J.J. Waterston used to derive this really important result. And remember, what we had was Waterston's idea was that you can treat each gas molecule like it's this little superball, and it's just bouncing around at these high speeds, bumping into the other superballs and the walls of the container, and then just bouncing off again. So he was able to, using that model, derive the law that gases have to follow if this is what is actually going on. Okay, if his model has some reality to it, and then by comparing back to the old gas law, he could draw certain conclusions. So let's just start by reviewing that. What was the old gas law? Okay, that's Charles' law. And what Charles said was that you have the pressure times the volume is proportional to, now let me write it this way. And I'll have something to say about what I mean by this amount of gas times the temperature. Okay? Now, what Charles and other people knew at this early stage was obviously the pressure and the volume of the gas depends to some extent on how much gas you have. For instance, if you hold the volume the same, keep the temperature the same, and just inject more gas into your container, obviously the pressure has to go up, right? So clearly, by increasing the amount of gas you have, you're going to increase the pressure or the volume. So there is this dependency in addition to the dependency on the temperature. Now, the problem is that unless you're thinking in terms of atoms, it was hard for them to quantify exactly what they meant by amount of gas. I mean, if they considered a particular gas, let's say they had oxygen, they found that if they kept the temperature the same, say, and let's say they keep the pressure the same, but the volume can vary, say the gas can expand. Well, if they double the amount of gas, the volume will double. Okay, but what if, so that's if they compare, if they have the same amount of gas and they vary the volume, there's this direct dependency. But then how do they handle the fact that, say, different, the mass of gas here that will give you a certain pressure or a certain volume depends radically on the type of gas you have. See, if you have, well, let me just ask you, if you had equal masses of oxygen and hydrogen gas, okay, you got hydrogen in one container, oxygen in the other container, equal masses of the two gases. And let's say they're at the same temperature and the same pressure. Which volume is going to be greater? Daniel? Yeah. Hydrogen is going to be, in fact, the volume of the hydrogen gas will be 16 times greater. Okay? So it varies from gas to gas if you think about this amount in terms of mass. If you have a particular kind of gas, then then obviously it works, that if you double the double the mass of the gas, then you'll double the pressure or the volume. Okay, so that's what people knew about gases before Waterston came along and did his atomic analysis. Now, okay, so here's what Waterston derives using his simple superball model. So let me just call this Waterston's law. Let me just write it this way. Okay, and you tell me what this means. What's big N here? Troy?
Number of atoms.
Yeah, number of molecules, say. And Ke, yeah, the kinetic energy of each molecule on the average. So, if you just, now Waterston, comparing to what was already known before, looks at this law of his and he says, well, now I have an interpretation of what it means. You know, this amount of gas that they knew about before. It's just the number of molecules, and that explains why there is this variation from type of gas, from one type of gas to another, because one molecule weighs, a hydrogen molecule, say, weighs 16 times less than an oxygen molecule. Okay, so, and it's not the mass of the gas that really matters here. It's just the number of molecules. But that implies now, I mean, what does Waterston have to do if his law is going to be consistent with the experiments that prove this? He has to interpret the kinetic energy per molecule, the average kinetic energy of a molecule, as the temperature of the gas. Okay, so that's where we would, and that's just by way of review, basically. That's where we were. Now, assuming he accepts this idea that the kinetic energy, the average kinetic energy of the molecules is what we mean by temperature. That's what temperature is. Then what can he explain with that idea? So, what does this idea explain? Okay, and we started to list the things that it explained. And the first thing I put on the list was Charles' law itself. Okay, so obviously, if we accept this idea that we can equate kinetic energy with temperature, then Waterston's law becomes equivalent to, explains the experimental data that were summarized by Charles' law. Now, I also pointed out last time that that's like spending $1 to get $1, right? Because you've come up with this brand new idea that you have to accept in order to accept this in order to explain this one law. But if that's all you get out of your idea, then that's not so impressive. But we started to see that Waterston could explain some other things too. And the first thing I told you about was Avogadro's law. So why does Waterston's law explain Avogadro's law? Evan?
Because if you keep the pressure of the gas and the volume of the gas and the temperature at constant levels, then
Mm-hmm.
not the volume, but then
Right. The
then
pressure and the temperature.
pressure and temperature, then the volume is just proportional to the number of molecules.
Right. I mean, if you see all these experiments that Avogadro was looking at, the pressure and temperature of the gas was held the same. And what they found was that he could explain the results of all these gas reactions by just assuming that the equal volumes of gases had to contain equal numbers of molecules when you have the pressure and the temperature the same. Well, so that's basically what Avogadro's law stated. Well, you look at Waterston's law, you see, well, that has to be true. If you keep the pressure and temperature constant, if you double the volume, you have to have double the number of molecules. Okay, so explains Avogadro's law. Now, what about the Dulong-Petit law of heat capacities? First, what was the Dulong-Petit law of heat capacities? They discovered something about heat capacities. Troy.
That, all atoms have the same heat capacity, and it's just since there's more atoms in some.
Right, exactly. I mean, the way they put it was, if you compare the heat capacities of different materials, okay, remember they vary over a wide range. You know that, for instance, water and alcohol have much different heat capacities, but they looked, Dulong-Petit looked at a whole bunch of metals, for instance, and found that aluminum, for instance, has a much higher heat capacity than lead. But that's when you compare them like equal masses of aluminum and lead. If you take samples where the block of aluminum you have has the exact same number of atoms as the block of lead, they'll have the same heat capacity. That's what Dulong-Petit discovered. Okay, so now what does that have to do with what Waterston's idea here? Well, it's what Waterston says is that temperature is to be equated with the kinetic energy of those atoms. Now, when you heat something up, Neve, do you have an idea? Oh, when you heat something up, if each atom, no matter whether it's a lead atom or an aluminum atom, if on the average each atom increases its kinetic energy by the same amount, well then Dulong-Petit's law has to follow. If each atom absorbs the same amount of kinetic energy, then each atom should, that's what it means for an atom to absorb heat. And so each atom, on Waterston's view, what Dulong and Pettit really said was each atom increases its kinetic energy by the same amount when you heat up the material. Well, it turns out that you can show from Newton's laws that this is going to be true. That if you take a bunch of highly energetic atoms, say, that are moving really fast, okay, and you let them loose in a room full of, slow atoms, okay. Now, on Waterston's view, that would be mixing, say, hot air with cold air. Okay, the hot air is the fast molecules, the cold air is the slow molecules. If you do that, and you accept this superball model, that they're all just bouncing around and whacking off of each other, and you just let you mix a bunch of fast superballs with a bunch of slow superballs, and you come back an hour later. On the average, the superballs will be moving with about the same speed now. That the fast ones will bump into the slow ones. And when that happens, they'll transfer some of their energy to the slow ones, okay, and make them faster. Meanwhile, the faster ones will have slowed down. Okay, so that's what's actually, and you can show just with Newton's laws that things will reach an equilibrium state where all the superballs have about the same energy. And that's exactly what's going on with the atoms here. So just using Newton's laws of motion and interpreting the kinetic energy as heat, Waterston can explain why Dulong-Petit's law has to be true. That same number of atoms absorb the same amount of heat. Okay. Now what about, let me see, what do I call this? Joule's say conversion of external motion to heat. Now, what did, I'll just remind you briefly what Joule discovered here. He discovered that if he hooked a weight up to a pulley, okay, remember, and the pulley turned the paddle wheels in his water, stirring up the water as the weight fell down to the floor. He found that if he dropped a certain weight through a certain distance, okay, the amount of heat that he generated in his water was equal to the weight multiplied by the height that it dropped. Okay, remember that? That wasn't so long ago. Now, now this turns out it fits in perfectly with Waterston's idea, because I told you that if you drop a weight through a certain height, h, okay, after it's dropped by h amount, the weight times the height how is that related to the speed after it's dropped a certain amount? Do you remember I told you that it's just the kinetic energy of the thing, right? It's this 1/2 the mass times the velocity squared. Okay, so that's how much external motion is created when you drop a weight through a certain height. Well, what Joule has done is he's taken this amount of external motion and he's transferred it into internal motion, right, of the atoms in the water. That's what his whole paddle wheel apparatus was just designed to do that. So this is how much external kinetic energy he had, energy of motion. That's how much he's putting into the water. He's just distributing it among all these water molecules. So that fits in perfectly with Waterston's idea that the increase in temperature that Joule was measuring is just an increase in the kinetic energy of the water molecules. Okay, now finally, I have one more item that I think is important enough to mention on this list of things that Waterston's law either explains or sheds a lot of insight into, that connects with in an important way and leads to this one idea making all of these things intelligible in a way that they weren't before, connecting them. Now, the last thing on this list is what I mentioned, the very last thing I mentioned in last week's class, which is has to do with the speed of these molecules. Now, if Waterston is right here, he can actually use his law to calculate what the speed of these molecules has to be. You all have this on your notes now, so let me get rid of it so I can work with a clean board here. So let's start over. Okay, so this is 5. And let's just call this relation of speed of molecules to speed of sound. See, physicists already knew the speed of sound at this point. And they, in fact, I've actually told it to you before in this class. Does anybody remember roughly what it is? Think of it this way. The way to think of this is there's a standard rule that a lot of people know about thunder and lightning. If you see lightning strike, and then, let's say, 5 seconds later, you hear the thunder, how far away was that lightning stroke? Drew?
Is it like 5 miles or?
It's 1 mile per 5 seconds, roughly. So if you see the lightning strike and you hear the thunder 5 seconds later, the lightning struck a mile away. Okay, so what does that mean? Nick?
Like 1,000 feet per second.
Yeah, exactly. It means since there's a little over 5,000 feet in a mile, and if it takes roughly 5 seconds for you to hear the thunder, that means the sound must be traveling at about 1,000 feet per second. So that's the speed of sound. Now, if we have this atomic theory of gases, what is sound? I mean, sound is got to be related to the movement of these molecules, right? I mean, what are you doing in a sound wave? If you think of let's say we have a big drum, okay, and we beat on it. Okay, how is that creating sound? Well, what we're doing is the drum membrane, right, is vibrating. And it's pushing these air molecules around. And it pushes some of them together. Let's say when the drum membrane pushes out, okay, it's pushing some air molecules together, so you get an area where you get a whole bunch of air molecules and then you have fewer in the adjacent layer of air right next to it. Well, what's going to happen? This area that has this compressed air is going to expand into the area where there's fewer air molecules. And that's basically what a sound wave is. You get these little areas where you have compressed air, and it expands into the area next to it, and then that gets dense, and so it expands into the area next to it, and so on. Okay, but how fast this process takes place has to depend on how fast these air molecules are moving on the average, right? So there should be a fairly close relationship between the speed of sound and the speed of the molecules. This whole process of the movement of this little pressure wave in the air, you would expect, maybe due to collisions, that's a little slower than the actual speed of the molecules. You wouldn't expect it to be faster. But you wouldn't expect it to be tremendously slower either. So you ought to get a number for the speed of these molecules that is maybe just a little faster than the known speed of sound. If you get something that's 100 times different than the speed of sound, then something's wrong. And maybe that's an indication that Waterston is way off base here and his whole analysis is wrong. Okay, so let's figure out what the speed of the molecules is according to Waterston. And it's not hard to do. Waterston's, remember his basic equation that he started with was just pressure times the volume equals the number of gas molecules divided by 3, multiplied by the mass of each molecule and its velocity squared. Well, we can rearrange this equation. Let's just write it over here. The velocity squared is equal to 3.
What is that?
Oh, this n?
Yeah.
Oh, that's the number of molecules. I'm just rewriting. This is Waterston's basic equation that he started with. So if we just rearrange here, with a little bit of algebra, I'm sure you can see that that implies that the velocity squared of these molecules is equal to 3 times the pressure times the volume divided by number of molecules times the mass of each molecule. Now, when you first look at that, you think, well, this isn't getting us anywhere because we don't know the mass of these individual molecules, and we don't know how many we have. Okay? But why doesn't that stop us? Troy?
Because we can do like up 1 mole as 1 gram of hydrogen.
Yeah, exactly. We don't know the mass, and we don't know N, but we know N times the mass because the number of molecules times the mass of each molecule is equal to the total mass of the gas, right? And we can just measure that. So we got lucky here. Okay, so everything in this equation is measurable. I mean, the pressure, the volume, and the total mass of the gas. So all you have to do is take the measurements, plug in the numbers, and actually I'll tell you what you get. For air, you get so let's just say speed of air molecules is equal to, see, I'm just about 480 meters per second. Now, sound, actually, we used feet before, but if you put it in terms of meters, it's about 350 meters per second. Sorry.
Colder day then would, like, if it's a cold day, would sound travel slower?
Yeah. Now, remember, though, that to change it a lot, you would have to make it a really cold day because remember what this temperature is. We're using Kelvin scale, right? So on a typical day, you know, this number might be 293, say. On a cold day, when the temperature is at freezing, it's 273. Okay, so to really slow down, you know, sound a lot, you'd have to say if you got it down to 100 Kelvin, then you would really see a noticeable change. But you'd be a popsicle long before that. Okay, so it's not really noticeable for typical temperature changes. So now this makes a lot of sense all of a sudden. I mean, the fact that these numbers came out this way. Now, scientists at this stage, Waterston, he didn't know exactly why this one was 350 in relation to the 480 here. But it makes sense that the speed of sound you know, might be, I mean, the sort of the upper limit that you would expect the speed of sound to be is, you know, the speed of the molecules. I mean, it couldn't go any faster. I mean, since the speed of sound depends on just the movement of these molecules, you would think, well, it can't be any faster than the movement of the molecules. Now, it might be a little slower because there may be collisions might enter in some relevant way to slow it down a little bit. But you would expect it to be roughly of the same order of magnitude, and that's exactly what we see here. So this is another instance where Watterson's theory is making sense and connecting with things that scientists already knew. Now, there's one thing about this, though, that should strike you as a little odd. Does this number, is it higher than you expected, lower than you expected? I mean, think about it for a minute. What I'm saying is every air molecule in this room right now is traveling at over 1,000 miles an hour, if I make that conversion. Okay? Every air molecule that's bouncing off you right now is hitting you at like 1,000 miles an hour. Now, how long should it, let's say we have an air molecule way in the back of the room, and it starts heading in my direction. How long should it take to get here? I mean, not even the time to snap my fingers, right? So let's say, now does this connect with other things you know? Let's say Mr. Van Dam spots a trail of ants in the back of the room, and he whips out his handy can of Raid, and he sprays the ants. Okay, now Raid is pretty stinky stuff, right? Now you would think, I mean, if there's these Raid molecules in the room, and they're traveling at this fantastic speed, how long should it take before you start smelling that Raid? Boom, just like that. And as soon as Mr. Van Dam sprays those ants, you should be smelling the stink of that Raid. You would think. Now, does that happen? No. Right? I mean, you'll smell it, but if I'm standing way up here at the front of the room and the Raid was sprayed at the back, it'll take maybe a minute before I start to smell it. Nick? Yeah, so what happens to them? They bounce off those air molecules, right? Yeah, see, that's good, Nick. That's exactly what's happening. That's what, see, when physicists first got this result, their first reaction was, that is way too fast, and it's inconsistent with what we know about diffusion of gases, because we know, I mean, if I just continue with the Raid example, that if we spray Raid in the corner of a room 20 feet away, that it takes time for the smell to get to us. I mean, it's actually a pretty slow process, gas diffusion. So how could they possibly be moving at hundreds of meters a second? Well, it's exactly what Nick said. It's because a Raid molecule that starts to move in my direction doesn't get very far before it whacks into an air molecule and heads off in some other direction. So let's think about this for a minute. Here's the picture to keep in mind. Let's say, well, let's put it in terms of something that we can see, so it's easier to visualize. And here's the parallel I came up with. Let's say that we have the Roman Colosseum here. And we've got the lions ready to let loose, and we put JJ in the center here. Okay, now JJ's got all his friends in the front row around here. And if he can make it to the edge, one of his friends will pull him up, and the lions won't get to him. Now, we're going to start him in the center, and we're going to blindfold him. Okay, and we tell him, well, we're going to release the lions in, let's say, we're not going to release them for 5 minutes. Okay, so he's got plenty of time to get to the edge, right? But here's the complication. Every time he takes a step, we're going to stop him, spin him around, and then he can take another step. But he doesn't know the direction of that second step with respect to his first step. Okay? So you can see that even if JJ takes his steps quickly, it's going to take him a while to get to the edge, right? Because he takes a step, let's say his first step, he takes in this direction here. Stop him, spin him around. Okay, he wants to step toward the edge, of course, again, but he doesn't know which direction that is. So in the second step, he ends up in that direction. Now he gets lucky with his next step. He goes in the right direction toward an edge, but then his next step, he ends up over here. So he ends up doing this zigzag thing. And it may only be 30 steps from the center to the edge, and he may have to take 1,000 steps in order to get there because he's not going in the right direction all the time, right? So this is exactly what's happening with the molecules in this room. Now what can JJ do to improve his chances here? Well, yeah, we're not going to let him do that. In terms of his steps, what should he try to do? Yeah.
Maybe mark his steps, like if it was in the sand, if you were to.
Oh no, you're thinking of ways he can cheat. Yeah, we're not going to let him cheat.
Oh.
Okay. But say.
Have one of the people
Yeah, yeah, have the people yell. Well, let's say we're all yelling, so he still doesn't know which direction to go. No, what would happen? One smart thing that JJ could do is, what? You got an idea?
I'm not sure, but by air, if you could feel which way the wind was blowing, maybe.
Oh yeah, no, all those are good ideas. But I'm not going to let you say those things because they don't apply to my gas molecules parallel here. Because the gas molecules can't rely on the air, on the wind. So, Sayla?
maybe if there's like a smell coming from a certain place by the edge.
No. How about this? What about he makes each step as big as possible? Okay, he should stretch out his stride, right? Because the even if he's put it this way. What if instead of the way I've drawn it here, JJ's taking huge strides. So the first step takes him to here. Okay? Now the second step still may be in a completely wrong direction. May put him over here. And the third step here. But you can see that on the average, as he takes more and more steps, on an average, he is going to be getting further away from the center. And it's going to take him fewer steps to get to an edge if his steps are larger. Okay? So the step size here matters. Now, what else matters?
Well, how big? How far?
I mean, we're only giving him 5 minutes total. Okay, so should he dawdle with his steps? Quick steps. You try to make the steps fast as possible, and as large as possible. That's gonna minimize the time that it takes for him to get to the edge. So, I mean, applying this kind of reasoning to the gas molecules in the room, we know how fast the gas molecules are moving. Watterson's already been able to figure that out. The air molecules in the room are moving at 480 meters per second. But how long do they go before another air molecule stops them and makes them head in another direction? In other words, that they bounce off another air molecule. That's going to be directly related to how fast they can get across the room. Okay, so we're going to use that analysis to derive some interesting stuff this afternoon.